I'm going to guide you through a ReSolve Maths by Inquiry task. So I want you to follow along with me as I move from slide to slide, and I will talk to you about what is contained on each slide and also give you some further instructions or some further thoughts. So the first image is that of a bumper car ride. What do you notice? I notice that even though the cars drive around in a circular fashion, that the bumper car ride is actually made of a rectangular shape. So the rail on the outside is actually rectangular and it's made of straight sides. So that's one of the first things that I notice. The question you're going to think about firstly today is that the rail around the outside of a bumper car ride is 50 metres. So that means the rail the entire way around the rectangle is 50 metres. Another way of saying this is that it has a perimeter of 50 metres. The length of each side is a whole number. So there's no decimal numbers. Each length is a whole number. What is the area of the floor of the bumper car ride? Is there more than one answer to this question? To answer this, what you need to do is you need to, in your grid book, find a rectangle that has a perimeter of 50 metres. Remember that a rectangle has two pairs of identical sides. So you need to find two pairs of numbers that when added together equal 50. Can this be done in more than one way? When you've found a rectangle that matches the criteria, I want you to calculate the area. You need to do that by multiplying the length by the width. When you've got an answer, write it down. Now your challenge is, have you found all possible rectangles? Remember how I mentioned there might be more than one. I wonder how many there is. How will you know that you found them all? I know when I'm trying to solve a problem like this, I generally create a table to record my working out. I'm very methodical, so I'll go through and make slight adjustments each time. However, what I'd like for you to do is to find me at least 3 rectangles that are different but still have a perimeter of 50 metres. And I want you to calculate the area for each of these rectangles. If you're feeling like you'd really like the challenge, I encourage you to try and find all of the possible rectangles. I'm going to show you them all in a table on the next slide. Here is the table of all possible rectangles with a perimeter of 50 metres and then the matching area. So it starts with a length of 1 metre and a width of 24 metres. When you put those numbers together, you get 25, and when you double them, you get 50. So the perimeter is 50 metres. The area here is 24 times 1, which is 24 metres squared. As we go down, the numbers change. See how I've made an adjustment, a slight adjustment each time. By taking 1 metre from the width and adding it to the length, I've made a new rectangle with a different area that still has a perimeter of 50 metres. What do you notice about my area as we go? How are the numbers changing? Why might that be? If I was to create a graph of the length against the area, what do you think that graph might look like? If you're not sure, that's okay. I'm going to show you in the next slide. But if you think you could try and draw a rough version of this graph, I encourage you to pause this video and do that now. You should put the length on one side of the graph, the area on the other, and then plot some of these points. Here is the graph. What do you notice? Where is the graph highest? Where is it lowest? Describe the shape of the graph. What does it tell you? What is the highest point of the graph? Can you see it here? It's in between these 2 points. Do you notice where it is on my length? I wonder what shape this rectangle is that has a length of 12 and 13. It's very close to a square. What can I say about the area of a rectangle? What generalizations can be made about the area of rectangles with a set perimeter? Hopefully, you've discovered that as a rectangle becomes closer to a square, as in the sides become the same for each side, the same in length, the area is maximized. So the rectangle with the highest possible area with a set perimeter is actually a square. I've got an interesting video for you to watch next, which shows how honeybees make their hive and why they choose a hexagon as the shape. You don't need to do anything other than to think and make observations during this video. As far as completing this task today, I would like you to take a picture of all of the working out you did while you were watching this video. So show me your rectangles with your area and your perimeter, and if you attempted to draw the graph, please show me that as well.
Honeybees are fascinating creatures for a number of reasons. Their incredible work ethic, the sugary sweet syrup they produce, and their intricate social structure. But another reason is that honeybees are, in fact, excellent mathematicians. Scientists claim that tiny insects can calculate angles and can even comprehend the roundness of the Earth. But there's particular mathematical bee genius behind the most important aspect of honeybee life, the hive. Just like humans, bees need food and shelter to stay alive. The hive is not only the bees' home, but doubles as a place to store their honey. Since it's so central to survival, honeybees have to perfect the hive's architectural design. If you examine any piece of honeycomb, you'll see that it's constructed from tightly packed hexagonal or six-sided cells. Of all the possible designs, why do honeybees choose this one? To understand, you need to think like a bee. Bees need a secure place for their entire colony to live. Similarly, there needs to be a place where their nectar can be stored and ripened suitably, until it turns into honey. That means there's a need for some serious space efficiency. A good solution is to build little storage units or cells just big enough for a bee to fit into, which can also double as the containers in which nectar is stored, the bee's very own honey jars. The next thing is to decide what the little cells should be made out of. Bees don't have beaks or arms to pick up things, but they are capable of producing wax. The thing is, producing it is a lot of hard work. Bees have to consume 8 ounces of honey to produce just 1 ounce of wax, so they don't want to waste it. So, they need a design that allows them to store the largest possible amount of honey using the least amount of wax. What shape does that? Imagining for a minute that all bees had to attend Architecture Academy and go to math class. Let's say they asked their geometry teacher, what shape would give us the most space to store our honey but require the least amount of wax? And the geometry teacher replied, the shape that you're seeking is the circle, leaving the bees to return to their trial construction site and begin building their honeycomb using circular cells. After a while, some of them might have noticed a problem with their design. Small gaps between the cells. We can't even fit in there. That's wasted space, they might have thought. So, ignoring the geometry lesson and taking matters into their own hands, the bees went back to the drawing board to rethink their beehive design. One suggested triangles. We can use triangles, look, they fit together perfectly. Another bee suggested squares. Finally, a third bee piped up and said, pentagons don't seem to work, but hexagons do. We want the one that will use the least amount of wax and be able to store the most amount of honey. Yes, I think that's the hexagon. Why? It looks more like the circle than the others. But how do we know for sure? To find out, the industrious insect architects calculated the areas of the triangle, the square, and the hexagon and found that the hexagon was, in fact, the shape that gave them the most storage space. They agreed on an ideal size and returned to work. The space-efficient comb that is a bee's trademark today is probably the result of this trial and error, but over long periods of evolutionary history. However, it paid off. Peek into any hive, with your protective goggles and netting on, of course, and you'll see the end result, a beautiful, compact honeycomb that any architect would have been proud to design.